Hello, my dear friends. I am Professor D.G. Trivedi. I am teaching in this college since 1987. Almost 33 years of my teaching, I taught many subjects, but specialization in digital electronics and electrodynamics. In TY physics, I am teaching normally electrodynamics. Previously in FI, I was teaching a vector analysis and all that things. So, I'm giving you my brief introduction. I am a Jivite. I am a student of this college since 78 onwards. And then after, I'd work in All India Radio. Then I work in a TV station. And then I'd work as a professor in Narmada College of Science and Technology. And then I came to my mother institute, that is St. Xavier's College, Ahmedabad, since 1987. Dear friends, I am very much interested to teach you about digital electronics. In your paper, PPH 1802, there is one unit of digital electronics is there. In that unit, there is especially the logic family chapter is there. In this chapter, I am going to teach you TTL logic family and CMOS logic family mainly. This is my brief introduction about your subject. We are not teaching directly in the classroom. That's why I'm giving you my this teaching in this way online to you friends. Dear friends, I'm teaching you through this PPT also. So PPT as well as my video lecture, I am going to post on YouTube, and I will give the link to the Moodle. So you people can directly see through the Moodle. So when you click the link on the Moodle, you will go to the YouTube's and you can visualize complete lectures, which is going to be followed by quiz, some question related with this lecture. So if you answer that questions, that means your presence is going to be marked as well as you will get evaluated that quiz immediately and you will get the marks for the internal evaluations, friends. So I am going to take now the first lecture, that is digital logic families, lecture number 1. And in this one, now first we'll see your syllabus. Just a minute, friends. Now we are changing this video display to the PPT display, so you will understand your PPT through me. Dear friends, chapter number 14, that is digital integrated circuits. This chapter I am going to teach you, which is consisting of TTL logic family as well as CMOS logic family. This chapter is in the book Digital Principles and Applications by Malvino and Leach and Saha. This is the 7th edition book is there. What are the topics are there? The first topic is the switching circuits 14.1. Second topic 14.2 is 7400 TTL. 14.3 is the TTL parameters. 14.4 is the TTL overview. 14.5 is the open collector gates. 14.6 tri-state TTL devices. 14.7 external drives for the TTL loads, and 14.8 is TTL driving external loads. 14.9 is 74C00, that is CMOS logic family. In between 74 and 00, if there is a C mark is there, which indicates now the logic family has changed. That is CMOS logic family, which is utilizing N channel and P channel MOSFETs. 14.10 CMOS characteristics. 14.11 TTL to CMOS interface, and 14.12 CMOS to TTL interface. What is the meaning of this interface? That means one type of the gate may be the TTL, which may be utilizing it as a driver. So its output is connected to the another IC, which may be containing CMOS IC. So how they are going to be compatible to each other, how they can be connected, output of one type of the TTL is connected to the input of another type of the CMOS. And opposite to that, that is CMOS to TTL interface, that we are going to learn lastly in this logic families. Textbook related with this one is Digital Principles and Applications. This is the 7th edition, and which is written by Donald P. Leach, Albert Paul Malvino, and Gautam Saha. This book for the digital electronics, you can consider it's like a Gita, it is like a Quran, or it is like a Bible. So it is a very, very important textbook for you. Dear friends, our objective to study this thing is this. In this chapter, our first objective is explain how diode and transistor can be used as a electronic switches. Second objective, demonstration and understanding of the TTL devices, their parameters, how to drive them, and how to use them to drive external load. Then the third objective, be familiar with the CMOS devices and its characteristics, and understand TTL to CMOS and CMOS to TTL interface. These are going to be our objective particular for this chapter. Dear friends, first of all, you should know what is IC means. Just a minute, I am switching over the screen. Dear friends, you should know what is IC. IC means integrated circuits. And if there are various components like resistance, diodes, transistors, that is a bipolar junction transistors, that is NPN and PNP transistor, and N channel and P channel MOSFET, etc., which is going to be prepared or it is fabricated from semiconductor material. So if this component is an integral part of the semiconductor chip, so same semiconductor chip from which the diode, transistor, CMOS, that is MOSFETs, and resistance are going to be prepared, and they are interconnected, and a microcircuit is going to be prepared. The circuit is so small you cannot visualize them by your naked eye. So, and using the advanced photographic techniques, the circuit is going to be prepared, and that connection is going to be taken out on a dual in line. There are pins are there over which the connection is going to be there, and that way the integrated circuit is going to be prepared. Mainly there are two types of the logic families: transistor logic family and CMOS logic family. In a transistor logic family, also it is bifurcated. The first logic family which was developed was diode transistor logic family. You have studied from the 12th standard onwards that AND gate, OR gate, etc. can be prepared from diodes and resistors. And transistor is used to get the inversions, that is as a switch or inverter. So using the diode and transistor, the NAND gates, NOR gates, and other universal logic gates can be prepared. So this logic family is known as diode transistor logic family. Then there was a RTL logic family, that is resistance transistor logic family was there, which was operating at a lower voltage, approximately VCC is equal to 3.6 volt. So it is outdated. Then using a Zener diode for a noise immunity, etc. In industry, there is a HTL or logic family was utilized. HTL means high threshold logic family, which is immune for higher noise level. And that in that logic family, they utilize Zener diode at the inputs. That is specially designed for industrial purpose. Then in a transistor logic family was came into the picture, which was developed by Texas Instrument in 1964. That means the diode through which you are preparing AND gate on OR gate, which is also replaced by the transistors. And that way the transistor logic family was created. We will see here detail in TTL logic, that is called transistor logic family 7400 series. In this transistor logic family 7400 series, it is mainly operated with the power supply of VCC is equal to exactly 5 volt regulated power supply is required. And this power supply should be regulated and only tolerance of 0.25 volt plus or minus is tolerated. That means these ICs are working with 4.75 volt to 5.25 volt, that is the regulated power is required, voltage has to be required. In this one also there are two type of IC is fabricated by the Texas Instrument 7400 series, which is called commercial applications, operating at the temperature range from 0 to 70 degree Celsius, and it is operated with 5.25 volt to 4.75 volt in between only. Another one, that is 5400 series, which is developed for military applications and which is utilized for military applications and for the military purpose, because in militaries are at a very extreme high temperature or maybe at extreme low temperature, where the instrument should work for communication and all other things. That's why that tolerance and the temperature range is going to be larger, from minus 55 degrees Celsius to plus 125 degrees Celsius. That is the temperature range over which this 5400 series is operating. Slightly unregulated power supply, that means 5 volt plus or minus 0.5 volt, that is 4.5 volt to 5.5 volt, that is a tolerance for this military application ICs. So that is utilized for the military applications. Now we'll see the TTL circuits. We'll switch over to another one, that is in 1964 Texas Instrument introduced transistor logic family, which is in short known as a TTL logic family, a widely used family of digital devices. Now I'm giving you the advantage of TTL logic family. TTL is a very fast and inexpensive and easy to use. In this chapter, we discuss several types of TTL: standard, high speed, low power, Schottky, and low power Schottky TTL. So this way, there are 5 types of the TTL devices was developed by Texas Instrument, depending upon its need in the market. Standard TTL, we are going to learn first, then we'll see that the speed of operations can be increased, and that is known as a high speed TTL. Sometimes you require a low power dissipation, and for that 74L00 series that is low power TTL, was developed. Sometimes speed is very much required. That means the fast operation is required. For that, Scotty TTL was created, shown for S00 series. And in between, the compromising between these two, that speed of operation and power dissipation. Speed of operation should be larger and power dissipation should be minimal. Between these two parameters, it is compromised, and there is another series which is developed, which is known as a low power Scotty TTL, which is having a tolerable level of speed of operation as well as power dissipation. You will learn about the open collector and tri-state devices also, because these devices used to be buses, the backbone of modern computers and digital system. You know that in a computers and microprocessor etc. or a digital system, from CPU or MPU to different peripherals, there is a data is going to be transferred. That means from different peripherals to this CPU, or from CPU to different peripherals, data is going to be transmitted through the wires. And if this bunch of the wires are going to be individually utilized, then there is a lot of wiring is required and the circuit becomes very complicated. To avoid these things, there is a common communication path is going to be developed. And depending upon the requirement, one of the peripherals is at a time connected with the MPU or CPU. And this work is going to be done by tri-state devices and open collector devices in a TTL. That's why this type of the tri-state devices was also developed. And that is very important. We'll see in this particular chapter. Since TTL uses active low as well as active high signals, negative logic may be used as well as positive logic. You have studied that what is a positive logic and what is a negative logic. Positive logic means, see, logic is considered with low level and high level, 0 and 1. It is simulated with the binary 0 and 1. So, when the level is going to be, let us consider it is going to be 0 volt, is corresponds with the 0 level. Then plus 5 volt is considered to be high level, that is considered to be 1. So 0 is corresponds to 0 volt and 1 is corresponds to plus 5 volt, then it is considered to be positive logic. Opposite to this is considered to be negative logic. Positive OR gate is equivalent to negative AND gate, and negative AND gate, and positive AND gate is equivalent to negative OR gate. So that truth table is like the same. So this way you understand there is a active low as well as active high signals are going to be utilized in the transistor, and that's why sometimes positive logic as well as negative logic is going to be utilized. But not to be confused, so better we are going to study here with the positive logic only. Then we are going to study about the CMOS, how the CMOS is going to be prepared. See, in a CMOS logic family also, just a minute, switching the screen. In a MOSFET, metal oxide semiconductor field effect transistor, that is voltage operating device. Input impedance is infinite. Current is almost 0 because input impedance is infinite. That means V upon R, that comes the current. So input current is minimum. That's why the CMOS is going to be most useful in a battery operated systems. Now, there are P channel MOSFETs, there is a N channel MOSFET, and there is a CMOS MOSFET. Three type of the MOS technology was utilized. In N channel MOSFET, this technology is mainly utilized to prepare memory devices. P channel MOSFET was previously used, but because N-channel MOSFET is more faster, almost 4 times faster, and its power dissipation is less than P-channel MOSFET. P-channel MOSFET is almost outdated. Nowadays, only N-channel MOSFET, which is utilized for the memory devices, and by combining P-channel MOSFET and N-channel MOSFET in a complementary way. That means both the transistors are sits one upon other. They are connected in a series mode, and either of the transistor is conducting at a time, just like a normal bipolar junction transistor. You have studied push-pull arrangement of NPN transistor and PNP transistor. Either NPN transistor is conducting or PNP transistor conducting. This is called the complementary push-pull arrangement in a transistor. Similar kind of arrangement is prepared in a CMOS series. That is, the one P channel MOSFET and another N channel MOSFETs are going to be operated. That power supply is not 5 volt, but that power supply can have any voltage from 3 volt to 15 volt. That means it can operate as a VCC to 3 volt also. It can operate VCC up to the 15 volt also. Whichever your requirement is there, you can utilize that power supply for the CMOS series. And that's why that series is also going to be flexible for the power supply. That means slightly unregulated power supply also it can tolerate. So that way the complementary MOSFET technology is mainly utilized. That power dissipation is less and the speed of operation is also little bit less compared to the TTL. So that is a drawback compared to the TTL. TTL is faster than CMOS, remember. But still, because of the power dissipation is less, we are going to utilize that devices also. Now, dear friends, in a complementary metal oxide semiconductor, devices are chips that combines P-channel and N-channel MOSFET in a push-pull arrangement. Because the input current of a MOSFET is much smaller than that of a bipolar junction transistor, cascaded CMOS devices have very low power dissipation compared with the TTL devices. This low dissipation explains why CMOS circuits are used in battery powered equipment such as pocket calculators, digital wristwatch and portable computers. That means wherever we are moving the electronic devices, right, it is like a mobile, then you cannot have adapter and power supply plug 230 volt etc. So there we are utilizing battery operated equipment. And in that battery operated equipments, you have to see that the power consumption should be less. So in that kind of instrument, if it is a CMOS circuits are going to be utilized, that is going to be better because it is having low power dissipation. Since a knowledge of subject covered here is not prerequisite to any other chapter in the stacks, the material can be studied in a part or in a whole at a time. So, an understanding of Ohm's law and familiarity with the basic DC circuits are the only background needed here. So, dear friends, we don't require here other knowledge regarding the flip-flop, counters, you can say that registers and designing of the sequential logic circuit, etc. Only you should have the simple knowledge of how the DC circuits are going to be operating, what is the Ohm's law, etc. What is the voltage drop, how the current is going to be flowing, in which direction current is going to be flowing, what is the drop IR across the devices, etc. You know that is enough for understanding the TTL devices as well as CMOS devices. So we are starting with the first point, 14.1, switching circuits. The semiconductor devices used in digital integrated circuits, ICs, includes diodes, bipolar junction transistors, which is called BJT, and metal oxide semiconductor field effect transistor, which is known as the MOSFETs. The most popular transistor logic TTL in use includes the 7400 and the 74LS00 families. So nowadays, out of the 5 type of the TTL I told you, there is a standard TTL 7400 to drive a higher current capacity. That means to drive a relay etc., you need higher current, you need a higher fan out. That for standard TTL 7400 series is utilized, and conventionally 74LS, that is low power Schottky TTL series, is going to be utilized. Resistors, diodes and BJTs are the elements used to construct these circuits. The 74C00 and 74HC, HC means high speed CMOS 00, are the most widely used families constructed using the MOSFETs. These two families of the circuits are referred to as CMOS since they use two different type of MOSFETs. Virtually all digital ICs in use today are silicon. So in ICs, normally nowadays it is utilized silicon as a semiconductor material. The first device we are going to study is a semiconductor diode. The symbol of the semiconductor diode is nothing but, you know that there is a triangle and there is a line. Triangle indicates anode and line says cathode, and it is called a PN junction diode. The symbol of semiconductor diode, sometimes called a PN junction, is shown in a figure 14.1a. The diode behaves like one-way switch, that is, it will allow an electric current in one direction only, but the current cannot pass in opposite directions. So this is only one-way path. You can say that if you are going in a traffic, it is one direction flow is only possible. So the switch is open in one direction and switch remains closed in another directions. You can say that. We will use conventional current flow rather than electron flow, because in opposite direction to the electron flow, we have taken the direction of conventional current directions. And in a diode, normally when it is a forward bias, current is flowing. That means the anode is, which is a p type of material, and cathode, which is n type material. So p type material is connected with the positive terminal of the battery, and n type material is connected with the negative terminal of the battery. Then it is called a forward bias. Then the current is flowing in the order of milliamperes, and it follows a square law diode characteristics. So current is very high, and voltage drop across the diode when it is forward bias is 0.7 volt, 0.7 volt will be there. So this is a forward direction current will be there. Figure 14.1b shows the direction of the current through the diode. This is the forward direction. That means the current is flowing from anode to the cathode. That means triangle points the direction of the current. When the conducting current, a silicon diode will have a nominal voltage of 0.7 volt across its terminal as shown in the figure 14.1b. In this condition, the diode is said to be forward bias. Notice that the triangle in the diode symbols points in the direction of forward current and easy memory crunch. It is not possible to pass the current through the diode in other directions. The reverse direction. When the reverse bias, the diode will act as an open switch, as illustrated in figure 14.1c. Here you can see the figure here. This is the symbol of the diode A. Triangle is nothing but the anode, line indicates the cathode. When this triangle is connected with the positive terminal of the battery and cathode is connected with the negative terminal of the battery, the diode is forward bias. That means p-type material is connected with the positive terminal of the battery and n-type material is connected with the negative type of the battery. Then what happens? The junctions between P-type material and N-type material, which is called the depletion regions. That depletion region is going to be shortened. The width of the depletion region is going to be shortened and the electron can flow. And because of that, the conventional current is flowing from anode to the cathode, and that current is in the order of milliamperes. So that is called forward bias current is going to be there. So this direction is here is shown by the forward direction of the current. Now another way, if the battery negative terminal is connected to the p-type material, that is anode, and positive terminal of the battery is connected with the n-type material, that is cathode, that is called reverse bias connections. In this way, the depletion region is going to be wider and no current can flow in this diode. So what happens? The voltage drop across the diode depending upon whatever supply voltage is given, because the current cannot flow in this one. So there cannot be voltage drop across some resistance which is utilized to controlling this current. So IR is going to be 0. So voltage drop across this diode depending upon whatever the voltage is going to be applied. And this condition is shown here with the switch. You can see this switch. If the switch is going to be open, the current does not flow. That means the potential is going to be the same as the potential across the diode, that is VCC. In summary, when the forward bias, the diode conducts current and the voltage across the diode terminal is above 0.7 volt DC. Second, when the reverse bias, the diode will not conduct current. The voltage across the diode terminal depends on the external circuits. Now, we will see some example. We will understand the working of this diode. Example number 1. For each diode in figure 14.2, determine whether the diode is forward bias or it is reverse bias. Determine the diode current I in each case. See the first figure. In here, the positive terminal of the battery is connected through the resistance 1K to the anode, and negative terminal of the battery is connected to the cathode. So it is connected in a forward bias connections. So when it is a forward bias, the current will flow. Now question is that how much current will flow? Voltage drop across the diode is going to be 0.7 volt. So VCC minus voltage drop across this one, or you can say that VCC minus IR, I is the current flowing through this one, minus voltage drop across this one is equal to this potential. That is, you are utilizing Kirchhoff's second law, and that way you will generate these equations. The current direction is from plus 5 volt to the ground, and thus diode is forward bias. The voltage across the diode terminal is 0.7 volt DC, and the diode current is found to be I is equal to 5 volt minus 0.7 divided by the resistance 1 kilo ohms, that is equal to 4.3 upon 1 kilo ohms, that means 10 raised to 3 ohms. So that 10 raised to 3 comes into the numerator. So you can say that 4.3 milliampere current is flowing through the diode when it is forward bias. In a reverse bias, second conditions, if you see the second figure, here 12 volt is connected DC, but the positive terminal of the battery is connected to cathode through the resistance, and negative terminal is connected to the anode. So it is the reverse bias connection. Current I is going to be 0, so current cannot flow. So voltage drop across this one from this potential minus this potential, that is voltage drop across resistance IR, but I is going to be 0, so IR is going to be 0. So same 12 volt is going to be appear here with respect to the ground, and hence the voltage drop across the diode is going to be 12 volt, and it is working as a open switch. The current direction is from plus 12 volt DC to the ground. Thus the diode is reverse biased. The diode current is then 0.0 microamperes or milliamperes. There is no voltage drop across the 10 kilo ohms resistance, and thus the voltage across the diode terminal is plus 12 volt. Second device we are going to study is a LED, which is nothing but light emitting diodes. What is the difference between normal diode and light emitting diodes? When the normal diode, current flows through the normal diode when it is forward bias, but it does not radiate any kind of lights. It does not emit any kind of light. But in special design diodes, where you are connecting them forward bias, the light is going to be emitting, or it is shown a different type of the LEDs. You have seen that red, green, blue, violet, yellow, etc. LEDs are available, which is utilized as indicators. How it emits the light? What is happening actually inside this one? Actually, in a semiconductor material, different type of the impurities, arsenic, gallium, etc., phosphorus, etc., are going to be utilized in different proportions. So, because of this, the electrons will go from ground level, ground state to the excited state, and again when it releases the energy in the form of HF photons or Hc upon lambda, and it comes back to the ground state, and that way that energy Hc upon lambda, that lambda is whichever wavelength is going to be there, that normally falls between the range of 4000 angstrom to 20,000 angstrom, sorry, 4000 angstrom to 8000 angstrom, which is a visible spectra of EM wave spectra. And depending upon the wavelength, suppose it emits the wavelength of 6200 angstrom, then it is showing the red LED. If it is a 5500 angstrom or something, then it is showing green LED. If it is 5800 angstrom or something, it is showing a yellow LED. If it is a 4700 angstrom or something, it is showing blue LED, etc. So, depending upon which wavelength it emits, it is showing that color of LEDs. So, this way LEDs can be prepared. The symbol for a light emitting diodes is shown in a figure 14.3a. The arrow indicates light emission capability. The operation of LED is similar to that of ordinary diodes. When forward bias, it emits light in the visible spectrum and is thus used as an indicator. Like this one, the symbol is diode, plus there is this two type of arrow which indicates that a radiation is going to be there when it is forward bias. For different type of LED, you can see that here one for red LED 1.6, for yellow LED 2.2, and for green LED 2.4. Typical forward voltages are there. That means when it is forward bias, that voltage drop across these diodes are not going to be just like ordinary diode of 0.7 volt, but it is higher than that. For red LED, again the voltage drop will be 1.6 across the diode. For yellow LED, it is going to be 2.2, and for the green LED, it is going to be 2.6, 2.4, sorry. However, the voltage across the diode terminals, when forward bias VF somewhat greater than 0.7 volt DC. Typically, LED forward voltage given in figure 14.3b shows that varies with the color of the emitted light. The color of the emitted light depends on the elements added to the semiconductor material during the manufacturing. Now, we will see the example related with this one. The diodes in this figure 14.2a is replaced with a red LED. What is the diode currents will be there? The diode is forward bias and the voltage across its terminal is about 1.6 volt DC. The diode current is I is equal to, because VCC was 5 volt minus 1.6, that is going to be 3.4 upon 1 kilo ohms resistance, that comes out to be 3.4 milliamperes current will be flowing. So, dear friends, thank you very much. We are ending the first lecture here. Next time we will see about the bipolar junction transistor as well as MOSFET, how they are working and how they are operating as a switch in digital electronics. Okay, thank you very much, friends.